Atracurium. This market-busting drug will revolutionise how short surgical procedures unfold. This drug is shorter acting, more predictable, and more easily reversed than previous analogues. This is the first drug that can degrade without the need for metabolic processing due to its unique self-degrading properties. Renal issues? No problem. Liver dysfunction? Also not a problem. Atracurium is a non-depolarising neuromuscular blocking agent with its 15 to 30 minute duration of action being independent of liver and renal function. Fact, if you had 550 moles of Atracurium, it would weigh 20,000 times more than a light bulb. Eureka! In practice, before neuromuscular relaxants were commonly used, more dangerous methods of muscle relaxation were in use, such as deeper anesthesia and inhalation anesthetics. This often had dangerous effects on the cardiovascular and respiratory system. At this point, there was a gap in the market for relaxing the muscles without the added risk of such side effects. The use of a muscle relaxant, such as Atracurium, allows safer levels of general anesthetic with adequate relaxation of the muscles of the abdomen and diaphragm. The circle represents the products involved in modern practice of general anesthesia. These methods, in comparison to past, allow seriously ill patients to undergo complex surgery with less complications associated with the high dose of general anesthetic. An example of such procedure is intubation. Atracurium was used for intubation as it widens the airways of the respiratory tract via smooth muscle relaxation, which can allow surgical tubes to enter the tracheal lumen with ease and no muscular spasms. Atracurium is contraindicated in burns and strokes. In summary, the use of neuromuscular blocking agents allows better and safer surgical procedures. All drugs have side effects. Atracurium's side effects include facial flushing and hypertension, both of which are common. An uncommon side effect is bronchospasm, and skin redness and itching, mainly at the injection site, is unknown. The most notable side effect is hypertension, due to the effect of this histamine widening the blood vessels, causing a drop in blood pressure. To compensate for this, the heart rate increases. This is due to the action at acetylcholine receptors in mast cells. There is also a reduction in gastric motility due to the muscle relaxation. The metabolite londenosine is known to lower the seizure threshold, and it has the potential to build up in the body due to a long half-life and cause this effect. It does this via actions at the opioid receptors. However, this effect has never been seen when Atracurium is used with general anesthesia. There are critical groups in Atracurium that lead to its action. Remember the highlighted features, as this is key to understanding this drug's structure-activity relationship. As seen above, this drug works by binding to acetylcholine receptors at the neuromuscular junction, also known as the end plate. Due to its antagonistic action at this receptor, it prevents the endogenous ligand, acetylcholine, from triggering muscular contraction. As this is a non-depolarizing drug, rather than depolarizing, it does not cause the initial contraction and thus significantly reduces the risk of bradycardia, which is an abnormally slow heart rate of less than 60 beats per minute. Depolarizing drugs can also cause hyperkalemia, which is linked to some fatalities in children. As noted earlier, you can now see the structure of acetylcholine appears within Atracurium. This causes binding to the acetylcholine receptors. However, the large cyclic structures act as blocking groups, which causes it to exhibit its antagonism. The distance between the charged nitrogens, 1.14 nanometers, is key for binding at both the active site on the alpha subunits and the deprotonated off-site cysteine residue via ionic bonding. The general issues with the current muscle relaxants were dependent on type. Depolarizing drugs' main issues were within the side effects of the hyperkalemia and the cardiovascular effects. For both classes, depolarizing and non-depolarizing, the duration of action was a concern, as they were often lengthy, causing temporary paralysis, or they were heavily reliant on the liver and/or kidneys. The key features of the molecule are listed on screen. We will show you a series of lead compounds, and try to match some of the features of the lead compound, and we will show you what we thought. Feel free to pause the video at any time to do this. Tuberculin is also a non-depolarizing muscle relaxant. The structural similarities are the two quaternary amine groups at an appropriate distance apart from each other, 1.15 nanometers in tuberculin and 1.14 nanometers in Atracurium, and the large cyclic blocking groups. More specifically, benzoisoquinone groups, which consist of a benzene ring attached to a hexane ring, with one of the carbons substituted for an ammonium ion. The main issue with tuberculin is that it is very long acting due to it being metabolized slowly, which can cause a long recovery time, and this is a trend seen in many of the lead compounds we will come onto. Succinylmethonium is a depolarizer muscle relaxant. The similarities between the two molecules are the charged amine groups, the distance, however succinylmethonium is a flexible molecule, and the acetylcholine mimicking groups. The structure is almost identical to the backbone, separating the two large cyclic groups in Atracurium. However, there are some issues with succinylmethonium, such as its action cannot be reversed by anticholineesterases, and the metabolism, and thus duration of action, can vary in those with unusual amounts of cholinesterase, which can be due to organ failure or genetic variations. Succinylmethonium is depolarizing, and so it is subject to the side effects of depolarizing neuromuscular blockers, previously mentioned within the mechanism of action section. Pancurium is also a non-depolarizer muscle relaxant. The structural similarities are the two nitrogen centers, the distance between the amine groups. The steroid spacer provides a 1.09 nanometer distance between the centers. The issues with pancurium were that it had a long duration of action similar to tuberculin, but a better side effect profile. However, it does block the muscarinic acetylcholine receptors in the heart, causing tachycardia. It used a rigid steroid structure to separate the nitrogens at 1.09 nanometers, which can still interact with the cysteine residue, which is at 0.9 to 1.2 nanometers from the acetylcholine bonding site. Petylene only has the large cyclic groups in common with Atracurium, but was interesting for a different reason. Petylene undergoes a spontaneous degradation at an unusually low pH, and this has a very similar structure to tuberculin, so as an attractive candidate as the duration of action would be largely independent of the body's metabolism, and through chemical modification, the rate of this degradation can be changed so it has a short duration of action in the body. Petylene's muscle relaxant properties were known from medical folklore as it was used to treat epilepsy as an alternative medicine. Petylene undergoes a similar reaction to an aldol condensation due to the acidity of the hydrogen alpha to the methoxybenzene ring. In an aldol, such a hydrogen is alpha to the carbonyl. This acidity comes from the formation of a conjugated system formed in this product. The aldol reaction is shown above. If you would like to try and add the curly arrows yourself, pause the video now. The reaction is also in Atracurium and will be covered in detail in the metabolism section. But essentially, the base removes the acidic alpha hydrogen, allowing the formation of a conjugated system. The reason this hydrogen can be removed is because the conjugate base is very stable due to the formation of the above system. The tertiary amine at physiological pH would pick up a proton and become charged. The reaction in petylene happened too slowly under physiological pH to be clinically useful. Experiments to improve the rate at which the alpha hydrogen was lost were conducted at the University of Strathclyde with George Dewar and his team, and collaborations with Wellcome Laboratories. Electron withdrawing groups were added to petylene to try and increase the acidity of the alpha hydrogen. An example of such group were isoquinoline esters. These acted as electron withdrawing groups and still provide a conjugation after the loss of the alpha hydrogen. However, this change caused a loss of potency. After another series, it was realized that ester groups provided good electron withdrawing properties and suitably increased the degradation rate under physiological pH. In the end, Atracurium was composed of two large cyclic groups, which are charged nitrogen centers similar to petylene. The similarities can be better seen with petylene drawn in a different orientation, separated by a chain similar to that of succinylmethonium to give an appropriate distance between the charged centers and an acetylcholine mimicking compound. As you all know, the metabolism is what makes Atracurium unique, as it undergoes spontaneous degradation. However, in a healthy patient, this only accounts for 45% of the metabolism. The rest is degraded by non-specific plasmaesterases and excreted into the urine. I will now draw the mechanism of degradation of Atracurium. Although this is very similar to petylene, so it should be a good test to see how much you've learned, and be able to see if you can predict where the curly arrows will go. Feel free to pause the video, and when you're done, see if you're right. Okay, firstly, a basic catalyst will remove the alpha hydrogen due to its increased acidity, and the bond will break inwards to form a double bond conjugated with the carbonyl. The formation of this system is the key driving force for the reaction, as it is very stable. The amine group is lost as a leaving group, resulting in a loss of charge, and due to the loss, The distance between the nitrogens can no longer be maintained, thus there is a loss of action. The first step in the synthesis is an addition-elimination reaction between a diol, 1,5-pentyl to be exact, and an alkene with an acyl chloride functionality attached. The alkyl groups will act as nucleophiles and will attack the carbonyl compound, causing temporary breakage of the carbonyl bond, but ultimately this will reform and the chlorine will be eliminated. The reaction is likely to employ a base such as pyridine to prevent hydrochloric acid formation, as this can be dangerous in industrial scale reactions. The next step is a Michael or conjugate addition. The carbon in the double bond is a soft electrophile and can react with the amine group to produce a carbon-nitrogen linkage, producing the tertiary amine. The final step in the synthesis is a reaction with methylbenzene sulfonate, which gives the nitrogen an additional methyl group, and therefore their charge due to holding 4 bonds. This reaction occurs as the nitrogen lone pair attacks a partial positive methyl group. This is just a nucleophilic substitution with a more complex leaving group and nucleophile. Benzene sulfonate is a good leaving group, as the negative charge can be delocalized between the sulfur and 3 oxygens, meaning it has resonance stabilized charge. So what have we learnt in this video? In summary, Atracurium is a non-depolarizing neuromuscular blocking agent and is used in surgery. Atracurium has led to safer surgical procedures due to the lower dose of anaesthetic being required. It has a clinical advantage over others as it is inactivated quickly in vivo, independent of organ functionality, and also its actions can be reversed, meaning long-term paralysis is unlikely. The distance between the charged nitrogens, the acetylcholine mimicking group, and the large blocking groups is vital for action. The drug was discovered and developed from previous neuromuscular blocking agents and petylene in an attempt to eliminate the side effects and give appropriate duration of action.